just might regret that night for the rest of my days. I remember those soldier boys tripping over themselves to win our praise. I remember that dream like candlelight, like a dream that you can't quite place. But
in our lectures so far in this course, we've focused on some theoretical results about rational canonical form, invariant factors, minimal polynomial, and characteristic polynomial, and how they relate to each other. And in this lecture, we're going to focus on some more algorithmic questions about how you actually compute these things. So I want to start with an example that is an example from Dummett and Foote, but I want to present it a little bit differently. So let's consider these three 3x3 matrices with entries in Q, A, B, and C. The question is, are these matrices similar? So that is A similar to B? Is A similar to C? And is B similar to C? So we know at this point that two matrices with entries in a field are similar if and only if they have the same rational canonical form, which is the same as asking whether they have the same invariant factors. And we saw at the end of the last lecture that one way to answer this question is to diagonalize the matrix x times I minus m, where m is going to be either one of these, any one of these three matrices. So diagonalize meaning put it into its Smith normal form, where you have ones down the diagonal, and then you have the invariant factors in the lower right corner. But in the particular case of 3x3 matrices, we have a little trick. We saw in the last lecture that two 3x3 matrices are similar if and only if they have the same minimal polynomial and the same characteristic polynomial. So we can use this result in this special case where our matrices are size 3x3. Now, please keep in mind that once your matrices are 4x4 or larger, having the same minimal and characteristic polynomial is not enough to say that two matrices are similar. All right, so what are these minimal and characteristic polynomials? Well, the characteristic polynomial we can compute, it's a determinant of x times I minus m. And for A and for C, it's easy to compute the characteristic polynomial. What we get is this determinant is x minus 2 squared times x minus 3. Why is it easy to see that? Because when you take x times I minus a, you get an upper triangular matrix whose entries are x minus 2, x minus 3, x minus 2 on the diagonal, and similar for C. And we know that the determinant of an upper triangular matrix is the product of the diagonal entries. All right, but x times I minus b is not upper triangular. It looks like this. So you can check that I did the arithmetic correctly here. So how do we compute this determinant? This is a nice opportunity to practice a little bit. You can do cofactor expansion down the first column. So this determinant is x times this 2x2 determinant, which is x times 4 times x minus 3 minus 30 times 0. So I'm not even going to write that part. And then minus 1 times this 2x2 determinant, 4 minus 85, 0, x minus 3. So you get minus 1 times 4 x minus 3. And you can factor out an x minus 3 and then see that you get an x squared minus 4 from here and a plus 4, typo, a plus 4 here. And that factors as x minus 2 squared. So we can see that all three of these matrices have the same characteristic polynomial. So the next question is then, what are the minimal polynomials of these three matrices? And remember, the minimal polynomial divides the characteristic polynomial, and every root of the characteristic polynomial is already a root of the minimal polynomial. Why? Because the characteristic polynomial needs to divide some power of the minimal polynomial. So every irreducible factor of the characteristic polynomial also needs to be a factor of the minimal polynomial. All right, so there's two possibilities. Either the minimal polynomial is x minus 2 times x minus 3, or it is the characteristic polynomial x minus 2 squared times x minus 3. So how do we check? Well, one way to check is if the minimal polynomial is not this, it's that. So let's plug in the appropriate matrix into x minus 2 times x minus 3 and see whether or not that matrix is 0. So if you take b minus 2i times the matrix b minus 3i, you see that this is not 0. How do you show that a product of two matrices is not 0? You just need one of the entries to be not 0. So I will leave it to you to check this. Similar for c minus 2i times c minus 3i is also not 0. A minus 2i times a minus 3i is 0. And the easiest way to check that is to just multiply them. So you should check all of these things that you really believe me. And this completely determines the minimal polynomial. Here, we see that it's not x minus 2 times x minus 3 for b and c. So it must be the characteristic polynomial, x minus 2 squared times x minus 3. For a, we see that the minimal polynomial is x minus 2, x minus 3. And the characteristic polynomial is x minus 2 squared times x minus 3. And because these matrices are 3 by 3, knowing the minimal polynomial and the characteristic polynomial completely determines the invariant factors. All right, so the minimal polynomial is the largest invariant factor. The characteristic polynomial is the product of the invariant factors. So for b and c, there is a single invariant factor. It's only the minimal polynomial is the only invariant factor. And for a, we know the largest invariant factor is x minus 2 times x minus 3. And we know that the product of the invariant factors is x minus 2 squared times x minus 3, and that each invariant factor divides the next one. There's only 1 degree left over. There has to be one more invariant factor that is the quotient of the characteristic polynomial divided by the minimal polynomial. So there's one more invariant factor that's just an x minus 2. So we get x minus 2 and then x minus 2, x minus 3. So in conclusion, b and c have the same invariant factors. They are similar. A has different invariant factors from A and B. So A is not similar to B and B is not similar. Sorry, A is not similar to B and A is not similar to C. All right, so I'm going to pause and erase and talk about some other questions. So this answers a lot of questions about these matrices, but not all of them. We've seen how to answer this question about similarity of 3 by 3 matrices by computing the characteristic polynomial and minimal polynomial. But first, that's not always going to work when you're dealing with larger matrices. And second, that's going to leave some questions unanswered. So what do I mean that that's not always going to work? We've seen that once n is greater than or equal to 4, the minimal polynomial and characteristic polynomial of an n by n matrix do not always uniquely determine its invariant factors. So what can you do in that larger matrix case is we saw in the last lecture that you can compute the Smith normal form. This is the statement of theorem 21 in section 2.12.2, which says that you can use elementary row and column operations to diagonalize the matrix x times I minus m into this particular form where you have ones on the diagonal and then the invariant factors. So I'll show you how to do that in one example. But I also claim that this process of computing the Smith normal form by elementary row and column operations is going to answer some additional questions that just computing the characteristic and minimal polynomials won't answer for us. So first, I'll just show you how to do this in an example, and then I'll talk about what this gets you. So the example of x times I minus a, where a is a 3 by 3 matrix from the beginning of this lecture, is done out in detail in Dummett and Foote on page 483 to 484. So what I wanted to do was do x times I minus b and diagonalize this matrix. And there are usually many, many ways to diagonalize a matrix. The sequence of row and column operations that you do is definitely not unique. And I'm not claiming at all that this is the best way. This is the one that I figured out for myself. So I want to talk through it and talk about the thought process a little bit. OK, so x times I minus b. We have this matrix. And one question is, ultimately, we want to get some ones on the diagonal and then the invariant factors. And I immediately see a way to get a 1 in the top left corner of this matrix. I can switch the first two rows, and then I can scale this row by -1 to get this -1 to be a 1 up in the corner. So I'm going to do that here. I swap the rows. So you see the first row here is the second row here. And then I just took the new top row and I scaled it by -1. So I did 2 row operations together here. Why can I scale by -1? Because that's a unit in Q bracket F. All right, so why is it good to have a 1 in the upper left corner? Because now I can zero out the thing below the 1 by taking an appropriate multiple of the first row and subtracting it from the second row. So I'm taking x times the first row, subtracting it from the second row, and this is what I get. So I get a 0 here. I take minus x squared plus 4x, add negative of that to 4, and I get x squared minus 4x plus 4. And then this minus 30, I get 30x minus 85. Okay, so now we're in good shape because I can do some column operations. I have a column that's 1, 0, 0. So subtracting off an appropriate multiple of the first column from the second column and an appropriate multiple of the first column from the third column, I can just zero out the first row outside of this one. I also factored x squared minus 4x plus 4 here as x minus 2 squared. Okay, so this 30x minus 85 is kind of gross. I can take a multiple of the third row. I can't zero it out, but if I take 30 times the third row and subtract it here, what I get is 1, 0, 0, x minus 2 squared, 5, x minus 3. Okay, notice we're in a situation now where the first row and column are in a situation where we want to leave them that way. So we're going to have this initial 1 in the upper left corner, and we're never going to move that again. So we're just going to deal with the second and third row and the second and third column. All right, so now my question is, can I get a 1 in this entry here in some way? And I mean, I see that I definitely can because I have a 5 over here. So one thing I could do is I could swap these 2 columns, and then I could scale the column with the 5 in it by a 1/5. Might not be the most like elegant, nicest arithmetic you can do, but it's certainly going to work. So let's do that. So I'm going to swap these columns, and then I'm going to scale the second column by 1/5. And I get 1, 0, 0, 0, 1, x minus 2 squared, 0, 1/5 x minus 3, 0. And now I know that I can take an appropriate multiple of this second row to zero out the thing below the 1 in this second column. So what am I doing? I'm taking 1/5 x minus 3 times the second row and subtracting it from the third row. So what do I get? Now I have a 0 below this 1. I have an x minus 2 squared, and now I have this kind of awkward minus 1/5 x minus 2 squared times x minus 3. Okay, so that seems like it's bad news. But the good news is I have 0, 1, 0 now as my second column. So I can take an appropriate multiple of that column to get a 0 in the thing to the right of it. So let's do that. So now we're in very good shape because we have 1, 0, 0, 0, 1, 0, 0, 0, and then whatever this is, minus 1/5 x minus 2 squared times x minus 3. But we can always multiply a row or column by a unit. So let's just multiply by -5 to turn that minus 1/5 into a 1. And now we have 1s on the diagonal and then a monic polynomial. What this process is telling us is that the invariant factors of this matrix are 1, 1, x minus 2 squared times x minus 3. All right, so you can think about whether you would have done this diagonalization a different way. I'm going to pause and erase and talk a little more about what else we might want to know about this matrix. By diagonalizing this matrix, x times I minus b, we've seen that the invariant factors of this matrix are just the single invariant factor x minus 2 squared times x minus 3. So this is the minimal polynomial and the characteristic polynomial of this matrix. All right, so what's the rational canonical form of this matrix? It's the companion matrix of this single invariant factor. So if you expand this out, you can write down the coefficients, which allows you to write down the companion matrix, 0, 1, 0, 0, 0, 1. And then since the coefficients are minus 12, 16, and minus 7, we get 12, minus 16, and 7 going down here. So what do we know? We know that B is similar to its rational canonical form. So there exists a non-singular 3×3 matrix over Q, let's call it P, such that P inverse BP equals this companion matrix, this rational canonical form matrix. What is P? So let me back up and say that we already knew this from the beginning of the lecture by computing the characteristic polynomial and then checking which of the two possibilities for the minimal polynomial was actually the minimal polynomial for B. We could see what the invariant factors of B were. So we know that B is similar to this matrix in rational canonical form. But it's not clear how to find this matrix P. So what I'm going to show you in the next video is that process of diagonalizing the matrix x times I minus b lets you find this matrix P in a way where it's not at all obvious how to find this matrix P if all you do is this trick from the beginning that a 3 by 3 matrix is the invariant factors of a 3 by 3 matrix are determined by its minimal polynomial and characteristic polynomial. So there really is some advantage to that more complicated Smith normal form process. So I want to give one more example like that. Let's back up now and look at Q bracket X modules. So let's suppose that V is a three-dimensional vector space over Q, and T is a linear transformation from V to itself that gives V the structure of a Q bracket X module such that it is isomorphic to Q bracket X mod the ideal generated by this single invariant factor, x minus 2 squared times x minus 3. So we're saying that V, that this Q bracket X module has a unique invariant factor that is x minus 2 squared times x minus 3, just like up here. So what's one possibility? What's one way that could happen? Is suppose we have this V, we pick a particular basis E1, E2, E3, and the linear transformation T acts on the basis vectors in a way that comes from this matrix B. So TE1 will be 0 E1 plus 1 E2 plus 0 E3. TE2 will be minus 4 E1 plus minus 4 E2 plus 0 E3. And TE3 will be 85 E1 plus minus 30 times E2 plus 3 times E3. So why did I pick it this way? Because now the matrix of T with respect to this basis is the matrix B that we started with. So we know that the invariant factors of B and the invariant factors of T are the same. So B, we know it has the single invariant factor x minus 2 squared times x minus 3. So this particular linear transformation turns V into a Q bracket X module in such a way that this is the invariant factor decomposition. So what might we want to know? Well, I'll pause and erase, and then I'll write down some questions about this Q bracket X module. We have this linear transformation T, and we have one basis for V, such that the matrix of T with respect to this basis is our matrix B. But we know that there exists another basis of V, such that the matrix of T with respect to that new basis is the rational canonical form of B. Is that matrix that's similar to B. So what is that basis? What do we know? So we know that V is a cyclic Q bracket X module. I mean, Q bracket X mod, this ideal, is a cyclic Q bracket X module. So there's some single element F in V such that Q bracket X times F, that the cyclic Q bracket X module generated by F is all of V, and it's isomorphic to this particular quotient. So there's a single generator F of V as a Q bracket X module. Well, what about V as a vector space? F being a generator of V as a Q bracket X module means that F x dot V and x squared dot V is a vector space for V such that the matrix of T with respect to it is the rational canonical form of B. That there's some good choice of a generator for this cyclic Q bracket X module where, okay, what is the vector space basis? It's F x dot F, x squared dot F, or if you prefer, F T of F and T squared of F. So there is some F such that you take these three vectors and the matrix of T with respect to this basis is the rational canonical form of B. All right, so how do we find that F in terms of this basis that we started with? So again, if you start with this matrix B and you do this trick to see that the characteristic polynomial and the minimal polynomial uniquely determine the invariant factors of this matrix, I don't know how to get that to answer a question like this for you. But what we're going to see is if you keep track of the row and column operations in that process to diagonalize the matrix x times I minus b, that will answer this question for you.